In this lesson, we will discuss the Cauchy-Riemann equations. We will now discuss the Cauchy-Riemann equations, which help us determine when a complex function is differentiable. The Cauchy-Riemann equations are named in honor of the French mathematician Cauchy, who discovered and used the Cauchy-Riemann equations, and also in honor of the German mathematician Bernhard Riemann, who made them fundamental in his development of the theory of functions of a complex variable. So to develop these Cauchy-Riemann equations, we're going to assume that f is differentiable at a point z0. Suppose f is differentiable at z0. So the limit of as delta z approaches 0 of f of z0 plus delta z minus f of z0 all over delta z. We're going to assume that this limit exists. And we know that as delta z approaches 0 from any direction, we must get a unique limit. So if we assume that delta z approaches 0 along the x-axis, as we did in a previous example, then we see that delta z will equal delta x plus I times 0, because delta y will be equal to 0, and therefore f prime of z0 can be written as the limit as delta x goes to 0 of f of z0 plus delta x minus f of z0 all over delta x. And this is, by definition, the derivative of f with respect to x at z0. So the first partial derivative of f with respect to x. Now we're going to let delta z approach 0 along the y-axis. So then delta z will be 0 plus I delta y, and we have again the derivative of f at z0 will now equal the limit as delta y approaches 0 of f of z0 plus I delta y minus f of z0 over I delta y. And if I pull out a 1 over I from this limit, then we see that this equals 1 over I times the first partial derivative of f with respect to y at z0. So again, since limits are unique, we have that the first partial derivative of f with respect to x at z0 must equal 1 over I times the first partial derivative of f with respect to y at z0. So if we write f in its components, we see that the partial derivative of f with respect to x at z0 will equal the first partial derivative of u with respect to x at z0, so x0 comma y0, plus I times derivative of u with respect to x evaluated at x0, y0, and the 1 over I times the partial derivative of f with respect to y at z0 will equal 1 over I times derivative of u with respect to y plus I times derivative of v with respect to y at z0, and this will simplify to the derivative of v with respect to y at z0 minus I times the derivative of u with respect to y evaluated at z0. And we see that these two expressions must be equal, and therefore their real and imaginary parts must be equal. So the real part of the derivative of f with respect to x is the derivative of u with respect to x, and that must equal the derivative of v with respect to y. Similarly, the imaginary part of the derivative of f with respect to x is the derivative of v with respect to x, and this must equal minus the derivative of u with respect to y evaluated at z0. So these two statements are what make up the Cauchy-Riemann equations. So suppose f of z, which is u of x, y, plus I times v of x plus xy is differentiable, equal to x0 plus I y0. Then if we just proved the first order partial derivatives of u and v exist at z0, 0, y0, and they satisfy the Cauchy-Riemann equations. The derivative of u with respect to x must equal the derivative of v with respect to y, and the derivative of u with respect to y must equal the negative of the derivative of v with respect to x, where these partial derivatives are to be evaluated at x0, y0. Further, from our previous calculations, we showed that the derivative of f at z0 can be written as the derivative of u with respect to x plus I times the derivative of u with respect to x evaluated at z0. So let's look at an example of a differentiable function and show that its first order partial derivatives satisfy the Cauchy-Riemann equations. We've already seen an example of the polynomial function f of z equal to z cubed, and we found the derivative to be 3z squared for all values of z. So we know that f is differentiable on the whole complex plane, and that from the power rule, f prime of z equals 3z squared. So let's show that the Cauchy-Riemann equations are satisfied everywhere. Let's show that the Cauchy-Riemann equations are satisfied for all values of z. If I write f and its components, I can write z is x plus iy. So x plus iy, the quantity cubed, will equal x cubed minus 3xy squared plus I times the quantity 3x squared y minus y cubed. So the real part u of xy is x cubed minus 3xy squared, and v of xy will equal 3x squared y minus y cubed. So I take the derivative of u with respect to x, I get 3x squared minus 3y squared. The derivative of u with respect to y will be negative 6xy. The derivative of v with respect to x will equal 6xy, and the derivative of v with respect to y will equal 3x squared minus 3y squared. So from these calculations, we see that the derivative of u with respect to x equals the derivative of v with respect to y, and the derivative of u with respect to y equals the negative of the derivative of v with respect to x. And to demonstrate the formula for the derivative of z, I'm going to write f prime of z as the derivative of u with respect to x plus I times the derivative of v with respect to x, and this will equal 3x squared minus 3y squared plus I times 6xy. If I factor out a 3, I get 3 times x squared plus I times 2xy plus y squared, which does equal 3 times the quantity x plus iy squared, or 3z squared. So in our next theorem, we will show sufficient conditions for proving differentiability at a point z0. A function f of z equal to u of xy plus I v of xy is differentiable at the point z0 equal to x0 plus I y0 if and only if u of xy and v of xy are continuous at z0 and satisfy the Cauchy-Riemann equations at z0. So for the proof of the forward direction of this statement, we've actually already proven this. So we know that if a function is differentiable, we showed that its component functions satisfy the Cauchy-Riemann equations. And we know since f is differentiable at z0, it will be continuous at z0, and therefore the component functions will also be continuous at z0. So the rest of the proof of this theorem will be a bit technical, and it relies on proofs of continuity of real-valued functions of two variables, which might be seen in a multivariable calculus class. So we're going to assume that u and v are continuous at z0, and they satisfy the Cauchy-Riemann equations at z0. Now let delta z be equal to delta x plus I delta y, and consider the difference f of z0 plus delta z minus f of z0. So we're going to take this expression and we're going to eventually divide this by delta z and take the limit as delta z goes to 0. But first I'm going to rewrite this expression in its components, u of x0 plus delta x, comma y0 plus delta y, minus u of x0 y0 plus I times v of x0 plus delta x, comma y0 plus delta y, minus v of x0 y0. And now we're going to use differentials from calculus to rewrite this expression and this expression using the fact that u and v are continuous. U and v are continuous at z0. We can use differentials from Calc 3 to write u of x0 plus delta x, comma y0 plus delta y as u of x0 y0 plus the derivative of u with respect to x at z0 times delta x plus the derivative of u with respect to y times delta y plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 and epsilon 2 tend to 0 as delta x and delta y go to 0. And we can do the same thing for the quantity involving v. So v of x0 plus delta x plus y0 plus delta y will equal v plus the derivative of v with respect to x times delta x plus the derivative of v with respect to y times delta y plus two air terms, epsilon 3 times delta x plus epsilon 4 times delta y, where again these epsilons tend to 0 as delta z tends to 0. So in the expression f of z0 minus plus delta z minus f of z0, we're going to replace these two quantities above using these two differential statements. Then f of z0 minus delta z minus f of z0 will equal, it's kind of a mess, it's going to be the derivative of u with respect to x times delta x plus the derivative of u with respect to y times delta y plus I times the derivative of u with respect to x times delta x plus I times the derivative of u with respect to y times delta y plus the error terms epsilon 1 delta x plus epsilon 2 delta y plus I epsilon 3 delta x plus I epsilon 4 delta y. Now we're going to use the fact that the first order partial derivatives satisfy the Cauchy-Riemann equations. I'm going to rewrite the derivative of u with respect to y as negative the derivative of v with respect to x here, and I'm going to write the derivative of v with respect to y equal to the derivative of u with respect to x. So I'm going to use the Cauchy-Riemann equations now. So I wrote the derivative of u with respect to y as minus the derivative of v with respect to x, and I wrote the derivative of v with respect to y as the derivative of u with respect to x by the Cauchy-Riemann equations. So now combining terms involving the derivative of u with respect to x, I get the derivative of u with respect to x times the quantity delta x plus I delta y, and combining terms involving the derivative of v with respect to x, I get plus I derivative of v with respect to x times the quantity delta x plus I delta y, and combine the error expressions, we get epsilon 1 plus I epsilon 3 times delta x plus epsilon 2 plus I epsilon 4, the quantity, times delta y. Now we're ready to divide this expression by delta z, and we see that f of z0 plus delta z minus f of z0 over delta z will equal, well, in the previous line, delta x plus I delta y, that is equal to delta z. So when I divide this by delta z, I just get the derivative of u with respect to x the next term, similarly, when I divide by delta z, this will cancel, and I'll just get plus I derivative of v with respect to x, and we'll get plus epsilon 1 plus I epsilon 3 delta x over delta z plus quantity epsilon 2 plus I epsilon 4 times delta y over delta z. So I'm going to take the limit as delta z goes to 0, and we know that the epsilons go to 0 as delta z goes to 0, but the quantities delta x over delta z does that go to 0 or 1? Well, this expression will always be less than or equal to 1, since delta x is the real part of delta z. In absolute value, delta x over delta z will be less than or equal to 1. Similarly, in absolute value, delta y over delta z will be less than or equal to 1 in absolute value. So as delta z tends to 0, we see that this expression goes to 0 v with respect to x plus I times 0 v with respect to x and we see that therefore the derivative at z0 exists, and we've established the formula f prime with z0 equals derivative v with respect to x evaluated at z0 plus I times derivative v with respect to y evaluated at z0. This establishes the sufficient conditions for differentiability at a point. So we see that a function is differentiable at z0 if and only if its component functions are continuous at z0 and they satisfy the Cauchy-Riemann equations at z0. Let's look at an example. Let's look at the function f of z equals e to the z, which we can write in component form as e to the x cosine of y plus I times e to the x sine of y. So its real part is e to the x cosine of y, and its imaginary part, v, is e to the x sine of y. And these functions are continuous on all of C. The exponential function and the trig functions cosine and sine are continuous in all of C. The derivative of u with respect to x will be e to the x cosine of y. Derivative of e to the x is e to the x. The derivative of u with respect to y will be negative e to the x sine of y. The derivative of v with respect to x equals e to the x sine of y, and the derivative of v with respect to y is e to the x cosine of y. So see that the Cauchy-Riemann equations are satisfied for all complex numbers z. Thus, the derivative of z exists for all complex z, and the derivative equals the derivative of u with respect to x plus I times the derivative of v with respect to x, which equals e to the x cosine of y plus I times e to the x sine of y, but this is exactly e to the z. So we see that the derivative of z equals e to the z for all complex numbers z. Next, let's rewrite the Cauchy-Riemann equations in terms of polar coordinates r and theta. So if we have x equal to r cosine of theta and y equal to r sine of theta, then when we write f of z as u of xy plus I v of xy, when we take the derivative of u with respect to x, we'll use the chain rule, and we see that u being a function of x and y, and x being a function of r and theta, similarly y is a function of r and theta, then the derivative of u with respect to r will equal the derivative of u with respect to x times the derivative of x with respect to r plus the derivative of u with respect to y times the derivative of y with respect to r, and the derivative of u with respect to x is written like this, and the derivative of x with respect to r will be cosine of theta. Derivative of u with respect to y times the derivative of y with respect to r, which is sine theta. So we get the derivative of u with respect to r, so this is this formula. Similarly, the derivative of u with respect to theta will be the derivative of u with respect to x times the derivative of x with respect to theta plus the derivative of u with respect to y times the derivative of y with respect to theta, and we get derivative of u with respect to x. The derivative of x with respect to theta will be r times the negative sine of theta. I get a negative r sine of theta plus the derivative of u with respect to y times the derivative of y with respect to theta, which is r cosine theta. The same calculations will follow for the function v, so we can write the derivative of v with respect to r as derivative of v with respect to x times cosine of theta plus the derivative of v with respect to y times sine theta, and the derivative of v with respect to theta will be negative the derivative of v with respect to x, r sine theta, plus the derivative of v with respect to y, r cosine theta. So by the Cauchy-Riemann equations, if the derivative of u with respect to x equals the derivative of v with respect to y, and the derivative of u with respect to y equals the negative of the derivative of v with respect to x, we have the following. The derivative of v with respect to r will then equal negative derivative of u with respect to y cosine theta plus the derivative of u with respect to x sine theta, and derivative of u with respect to theta will be r derivative of u with respect to y sine of theta plus r times the derivative of u with respect to x cosine theta. Now we compare, we have that the derivative of u with respect to r will be equal to the derivative of v with respect to theta divided by r. So in polar form, we have the following. The derivative of u with respect to r equals 1 over r, the derivative of u with respect to theta. And from our calculations, we see that negative derivative of u with respect to r will be 1 over r times the derivative of u with respect to theta.